Hello. So in this video, we're going to try to find the slope of the graph of f of x equals x squared. And as you'll notice, I put that word slope in quotes. I'm going to explain in a minute or so why I did that. But just so we're on the same page, the slope of a line, and that's a word that's usually associated with lines, the slope of a line is some number that tells you something about the steepness of that line as well as the direction that it's going. In other words, how steep is the line and is it going up or is it going down as you look from left to right? So this single number called slope tells you that. And it's generally pretty easy to find on a line because lines have a constant steepness and direction, and so they have a constant slope. The way we find the slope then is we could pick any 2 points on that line. We could measure the slope using any 2 points. And we measure specifically the difference in y coordinates and divide by that corresponding difference in x coordinates. If you've done that in an algebra class, you may have heard the phrase rise over run. That's essentially what we're doing here. And I'm going to pop up an example of what I'm talking about here. Okay, so there's a graph of a line. And I've labeled 2 points on the line, the points having coordinates -2, -5, and 2, 1. And so I'm going to use those 2 points to find the slope of this line. So here I go. I'm going to say this. All right, the slope, as I mentioned, I'm going to take the difference in y coordinates, which in this case, the y coordinates are 1 and -5. So I'm going to take the difference in them, 1 minus -5. And I'm going to divide by the corresponding difference in x coordinates, which would be 2 minus -2. And let's see, when I simplify, in the numerator I've got 1 minus a -5, which is the same as 1 plus 5, which is 6. And then in the denominator I have 2 minus -2, which is the same as 2 plus 2, which will give me 4. And I could reduce that fraction. 6 over 4 gives me 3 halves. So 3 halves. So 3 halves would be the slope of that line. Okay. And again, I mentioned that phrase rise over run because if you look at going from that lower point to the upper point, in order to get there, I would rise, let's see, 1, 2, 3, 4, 5, 6 squares in the grid, and I would run specifically to the right, 1, 2, 3, 4. So to get from the lower point to the higher point, my rise was 6 squares and my run was 4 squares. So the slope is 6 over 4, which reduces to 3 over 2. Okay, so that's the slope of that line. Okay, great. So again, I would say the slope of a line, it borders on being boring. It's easy because lines have constant slope. The slope of a line is the same for the entire line as it is for any region of the line, as it would be for any single point on that line. It's a constant value no matter where you look, which is why you could use any 2 points on the line to do this rise over run thing that we did. Life gets much more complicated when you try to do that same thing with a nonlinear function because the graph is not a line, right? So problems ensue. For one thing, the word slope is kind of awkward because almost by definition, if the graph is not linear or not a line, then the slope is bound to vary. You're going to measure different slopes on different regions, and the slope may vary even on a point-by-point basis. So how do we hope to find the slope? We're used to using 2 points to measure it. What 2 points do we use? Right? So we run into some trouble, almost because it's not a line, right? So all bets are off. Our recipe for finding slopes of lines would completely fail us, it seems. Can we even find the slope of something that's not linear at a single point? So here's an example of the problem that we have in front of us, hence the name of the video. I have a graph of f of x equals x squared depicted, and I want to find the slope of that graph at the point 1, 1, which is the point pictured in green. So the reason I put that word slope in quotation marks in my title is because the graph of x squared does not have the slope. The slope of the graph of x squared varies depending on where you look. And in this case, it would actually vary on a point by point basis because, at some regions of the graph is falling as you look from left to right. At other regions of the graph is rising as you look from left to right. And the steepness is varying throughout. So it makes no sense to say the slope, but we can perhaps measure a slope at a particular point. Maybe, right? So that's what we're going to try to do. We're going to try to measure the slope of the graph at that point 1, 1, which we might reasonably expect is going to be different from the slope any place else on that graph. But we're going to try to find that slope. Now, you could imagine mathematicians dealing with this question for the first time. How the heck do you do it? They might have cried to start out with. How is it going to happen? But then they may have come to a revelation that, hey, maybe I can't find it at the point 1, 1. Maybe I can't find the slope there, but perhaps I got a shot at least at approximating it. Maybe I can approximate the slope at 1, 1 by taking the average slope of a region on the graph. So I would pick a region that's close to the point 1, 1 and find the slope there and say, well, okay, that's roughly the slope at 1, 1. By the way, when we talk about the average slope of a region of a graph, it would be the same as measuring the slope of the secant line that connects the endpoints of that region that we're talking about. And I realized just now that I'm using a lot of words when I say that. So I'm going to show you a little bit more what I'm talking about. So here's the approach I want to try to take. I'm imagining I'm the first mathematician that's done this. And I have no way of knowing how to get the slope at 1, 1. So what I'm going to do instead is I'm going to find the average slope bounded by the points 1, 1, which is the point I'm interested in, and 2, 4. I want to find the average slope of that snippet of graph, right? Now, as we look at the image, so the graph itself of x squared is in red, and we see that that graph has a varying slope throughout even as you go from 1, 1 to 2, 4. It's curving a little bit, so it doesn't have a constant slope. That slope is changing throughout. But I would argue that on average, the slope of that region of graph would be the same as the slope of that blue secant line. And so what I'm speculating is that the slope at the point 1, 1 is roughly equal to the slope of that secant line. By the way, I know because I've done it before, I know in advance that's not right. The slope, in fact, would be the slope of the tangent line or the line that touches the graph at 1, 1. So imagine that you've drawn this graph really big on some big blackboard. If you then get like a meter stick and you run that meter stick along the curve and you stop where the meter stick touches the point 1, 1, that meter stick would represent a tangent line that's touching the graph there, right? So the slope of the graph is actually the slope of the tangent line at the point, right? So I have the secant line, which we should be able to draw, and hypothetically, how the heck do we get this tangent line? Take it as a gift for now. I'll I'll track back to how we actually get the tangent line, but I wanted to depict the tangent line to say that our approximation is just that. It's an approximation, but it's off, right? But we got to start somewhere, so that's where we're going to start. We're going to take the slope of that secant line and say, hey, that's roughly the slope of the tangent line. So I will say that the slope at the point 1, 1 is about equal to the slope of the secant line. And that slope will be change in y, 4 minus 1, because those are the y coordinates, divided by the corresponding change in x coordinates, 2 minus 1. So I get 3 over 1, or just 3, right? The slope of that blue secant line is 3. So I'm saying that the slope at 1, 1 for the graph of x squared is about 3. That's my estimate, but I know it's off. It's a little bit off because my tangent line, as I can see in this graph, it's not as steep. So my estimate's off, and specifically, I know that it's a little too high. Well, can I do better? Well, maybe I can. Um, that 0.24 is maybe it's too far away from 1, 1. I might be able to do better if I pick a point that's closer to the 0.11 on the graph and find the average slope of that secant. So I'm going to try to do that. Let's see, I think I've just about run out of board space. So I'm going to go back to the top and then to the right a little bit. Okay, so here we go. So once again, I have an image of the graph in red. I've kept my blue secant line on the graph, the secant line that connects the points 1, 1 and 2, 4. But this time, I'm going to instead find the average slope of the graph between the points 1, 1 and that point that I labeled in green, 1.5, comma 2.25. So you can see that those 2 points are a little bit closer. Sloper. They're a little bit closer. So I'm going to use that as an approximation of the slope of the graph at 1, 1. Again, I'm using the black for my tangent line, but this time I'm going to say the slope of the tangent line is roughly equal to the slope of that green secant line. And as we can see, the green secant line, we can see visually that it's a better estimate of the slope at 1, 1 than the blue secant line was. So I think that's a good strategy. So we're going to go with that. We'll say that the slope at 1, 1, again, it's not exact, but it's approximately equal to the slope of the green secant line. And that slope would be the change in y values over the change in x values. So in this case, the y coordinates are 2.25 and 1 over the corresponding x coordinates, which are 1.5 and 1. And by the way, in case you don't know how we get the y coordinate, the function is x squared. So to get the y coordinate, you just take the corresponding x coordinate and square it. In other words, 1.5 squared gives you 2.25. So that's how I know that second point on my graph of f of x equals x squared. And for that matter, I know 1, 1 is a valid point because the square of 1 is 1. So anyway, so this fraction is the slope of my green secant line. Let's see, that gives me 1.25, and that's over 0.5. And when you do the division on that, you get 2.5. So the slope of my green secant line is 2.5, and I'm saying that that is roughly the slope of the graph of x squared at 1, 1. Again, it's not exact, but I know it's better than the blue secant line is, so I'm using that as my new estimate. Right? So it seems that that tack is working. So the 2 points I'm using, one of the points is the point at which I want to actually find the slope, and that second point is a point that's on the graph, and I'm bringing that second point closer and closer to the point in which I'm interested. And I'm thinking it's giving me a better and better and better estimate of what the actual slope is at 1, 1. So what if we take that logic to its ridiculous extreme? Um, in other words, what if we take the second point to be um, so close that it's almost imperceptible distance between them? We're starting to see, by the way, that our secant line is starting to look like the tangent line. And in fact, well, if you take the second point and bring it so close that it becomes the first point, then it really is just a tangent line. It's a line that touches the curve at the point of interest. Well, can we do that? Because the logic seems to dictate the closer the point is, the more accurate our estimate is. So if the second point is quote unquote on top of the first point, then it should be exactly the slope. But you may recognize that there's a problem with that approach. We run into a problem. Well, and what is the problem? Well, when you do the division, if you take a second point, but that second point is the same as the first point, when you calculate the change in x, there's no change. That makes the denominator zero. And so the fraction that determines the slope is undefined. So we can't put the second point on top of the first point. Right? We can't do that. Is there anything we can do? Fortunately for us, calculus says yes. What we can do is we could still use that average slope notion, but pick as our second point a point that's much closer to the point of interest. We'll say horizontally it's some distance delta x away from that first point. And then we take the limit as that value delta x approaches zero. So in the graph below, the red graph, it's almost like a brown, or sort of the brownish red, the curvy thin. That is the graph of our function. The black line is still the tangent line at 1, 1. I've kept the green secant line there, but I want to take the slope of that orange secant line that connects the points 1, 1, and the other point 1 plus delta x comma 1 plus delta x to quantity squared. You could see that the corresponding horizontal change, that change from there to there, that would be 1 plus delta x minus 1, or just delta x. So horizontally, the second point is delta x units away from the first one. I can't put the second point on top of the first point, but I could take delta x to go arbitrarily small. And if I find the limit of the slope of that brown secant line, or I guess I should say orange secant line, as delta x shrinks to zero, if that limit exists, that should give me exactly the slope of the graph at the point 1, comma 1. In other words, what I want to do then is I'm going to say that the slope of the graph of x squared at the point 1, 1, it's no longer going to be an approximation. It's going to be equal to the limit as delta x goes to 0 of the change in y over the change in x for the 2 points 1, 1, and 1 plus delta x comma 1 plus delta x, the quantity squared. In other words, I'm going to take the limit of the change in y, which would be 1 plus delta x quantity squared minus 1 squared, which is just 1, divided by the corresponding change in x, which is 1 plus delta x minus 1. Now, the denominator, that simplifies pretty easily because the 1's cancel out. That numerator, when you expand that, that's really 1 plus delta x times 1 plus delta x. You could FOIL that out, and you get 1 plus 2 delta x plus delta x, the quantity squared, still have minus 1. And the denominator is delta x. And we're still trying to find the limit. In other words, does that fraction approach anything specifically as delta x gets closer and closer to 0? We're still trying to find the limit of that fraction. Now, one thing that we see is that numerator can be simplified a little bit more because the plus 1 minus 1, that cancels. So what we have left in our numerator is 2 times delta x plus delta x squared. Um, delta x is a common factor of that numerator, so I'm going to factor that out. So here I go. I'm going to say delta x, and then when I factor delta x out of that numerator, I'm left with 2 plus delta x, and that's over delta x. And I'm still taking the limit of that fraction as delta x goes to 0. And I see things simplify a little bit more because delta x is a factor that's common to both numerator and denominator, so I can cancel it out. So I'm taking the limit of 2 plus delta x. That's pretty easy. At this point, I could just substitute 0 in for delta x to get that limit, and that limit comes out to be 2. So since that limit does have a specific value, I can say that the slope of the graph of x squared at the point 1, 1 is exactly 2. We saw that it was approaching 2. You know, when we did our first approximation, we got 3. Our second approximation was 2.5. So it was getting closer and closer to 2. But as it turns out, that is exactly what the value of the slope is there. Okay. So remember, so I drew a black tangent line. How did it get there? Well, it's because I knew that eventually I was going to be able to find that slope. And then once you find the slope, then you could use Algebra 1 methods. You could use the slope-intercept form or the point-slope form to find the equation of the line, right? The slope is 2. A point on the line is 1 comma 1. So you could find the equation of the line. The equation of that tangent line is y equals 2x minus 1. So there you go. Okay, that's nice, but can we do better? Can we generalize that result? In other words, so we found the slope of the graph at the point 1 comma 1. Can we, in general, come up with an expression for the slope of the graph of x squared at any point on the graph a comma a squared? Well, I think we can by taking a similar approach. We will take our point of interest being a comma a squared, and we'll pick a point that's ideally not too far away, um, like the point a plus delta x comma a plus delta x, the quantity squared. We'll take that point and then get the slope, in this case, of the black secant line. So the slope of the graph at a comma a squared is the same as the slope of that blue tangent line. We're going to take the slope of the secant line, but then find the limit again as delta x goes to 0 and see what we get. So let's give that a shot. So I'm going to say the slope of the graph f of x equals x squared at the point a comma a squared is exactly equal to the limit as delta x goes to 0 of the slope of that black secant line, which would be the change in y, a plus delta x quantity squared minus a squared divided by the corresponding change in x, which will be a plus delta x minus a. Now, by the way, we're finding the slope at a comma a squared, so essentially the thing that I'm calling a is an x coordinate of whatever point on the graph of x squared, right? Okay, so the denominator, that simplifies pretty easily because, again, you can cancel these values. So it looks like our denominator is just delta x. But now for our numerator, a plus delta x, the the quantity squared. That's a binomial. That's a plus delta x times a plus delta x. When we FOIL that out, we get a squared plus 2a delta x plus delta x squared. And then we still have minus a squared in the back. And we're still taking that limit as delta x goes to 0. Okay. And let me lengthen that fraction bar a little bit. All right, so we see in the numerator, the a squares cancel out. And in the terms that are left in my numerator, I see that delta x is a common factor. So I can factor it out of that numerator. When I do, I end up with 2a plus delta x. In other words, that numerator factors into that product that I've just written down. And of course, I still have delta x in my denominator. And then, so I'm trying to take this limit, and it looks like I can simplify because delta x is a common factor to both numerator and denominator, so I could cancel those out. And now to find that limit, I could just set delta x equal to 0. And when I do, I get 2a, which means that the slope of the graph of f of x equals x squared at any point on that graph, a comma a squared, is 2 times whatever a is, or 2 times whatever the x coordinate is. So let's check to see if that works out for us. Well, we found that the slope, let's get my bearings here. Yeah, we found that the slope of f of x equaling x squared at the point 1 comma 1. Remember, we found that that was 2, right? So 1 comma 1. We found that the slope at 1 comma 1 was 2. But according to what we just found, it should be 2 times that x coordinate, which is 2 times 1. Yeah, sure enough, that gives us 2, right? Now, what if I took a different point? So I want to find the slope of f of x equaling x squared at the point 2 comma 4, right? So that's further up on my graph. I'm going to try to put it down. So here we go. There's that point 2 comma 4, right? I just marked it as a blue dot. That's higher up. You can see that the graph is a little bit steeper there. So I'm expecting that slope to be higher. But it's 2a regardless. In this case, a is 2, so I get 2 times 2, which is 4. So sure enough, I'm getting a higher number for that slope. And it confirms what we perceive visually, which is the slope of x squared is obviously different depending on where you look. And it should be steeper the further up and to the right you go. And sure enough, that's what we're finding. Well, what about the slope of f of x equaling x squared at the origin at 0, 0, right? Well, if we look there, we shall see, again, we talked about the slope being a tangent line at the point 0, 0. And there's my worst impersonation of a tangent line you've ever seen. But I'm thinking that's what the tangent line there looked like. It doesn't look like it has any steepness at all. So I'm thinking the slope there should be 0. But again, the slope is 2 times a. Right? Here's our point 0, 0. So a is 0. Right? So our slope is going to be 2 times 0, which is just 0. And sure enough, that's what we're getting, right? And we'll do one more. If instead I want to find the slope, say, at -2, 4, which puts us there. So we see in this region of the graph is going down as we look from left to right, which means that the sign of the slope should be negative. We should have a negative slope there. Let's see what happens. if I find the slope of f of x equaling x squared at the point -2, comma 4, it's still 2a, where in this case a is -2, so that slope is going to be 2 times -2, which is -4. So there we go. So we see that, in fact, there is a hope of finding slopes of curvy things, right? In this video, we found the slope of, specifically of the graph of f of x equals x squared. I want to see in a subsequent video if we could generalize that idea even further. Because if we can, then I think we found something that's pretty profound. So that's something that we have to look forward to in a subsequent video. Well, and I guess I forgot to introduce myself in the beginning. So in case you don't know, this is my channel. I'm the Math King. I'll see you around. Bye.